We have now reached the lowest level of the hierarchical organization. In this module, we will look at the neural circuits that control muscles and explain how each of these muscles bring about different responses, whether it be reflexes or voluntary movements. Muscles, which are made up of multiple muscle myofibrils, these are little strands that you're able to see if you've ever paid attention when you're eating chicken. Sometimes you could pull it apart, and that basically is what makes up the muscle. Please note that our motor units are comprised of a motor neuron and muscle fibers that it innervates. That is to say that all muscle fibers contract when a neuron fires. You may remember in chapter 1 we looked at how the size of the brain seems to be consistent more so with the size of the body. And when we looked at the size of an elephant, we know that they have a much larger brain than that of a human, but it is so because of their limbs. The limbs are so heavy, and so every time a motor neuron fires, then the muscle fibers contract. Now, if you have a very small motor neuron that is trying to control such a heavy limb, it is possible that the movement would be compromised. The number of fibers that exist per unit varies from muscle to muscle. And we find that the more control we have, the more precise, the more fine control we have, the fewer fibers and neurons that are there. Think of the muscles that you have in your fingers, which can move in various ways, in comparison to the muscle fibers that you would have in your hamstring or in your quads, which are very large muscles. Despite the fact that you'd have a lot more fibers in your thighs, you cannot do much with them. Whereas with your fingers, where have fewer fibers, you could do various tasks with them. The muscle fibers, again, are bound together by a tendon, and whenever there are contractions, we find that this is the only method we could generate a force, but this is caused by the release of a neurotransmitter, more specifically acetylcholine. This neurotransmitter by motor neurons at the neuromuscular junction would allow the body to engage in a response, whatever response may be appropriate. Please continue tying this to the previous modules as it is all connected, because the acetylcholine would have actually been released as a response from what the brain thought was appropriate. So it came down from the association cortex to secondary to primary to midbrain to the spinal cord, and now we are seeing the muscle responding in a way to keep us safe. In our body, we have smooth muscles, and smooth muscles are examples of that could be like your uterus or your intestines. These cannot be worked out per se, like a skeletal muscle. A skeletal muscle would be found in your skeleton. It would be an example that could be like your biceps or your quads. We also have a cardiovascular muscle, and that's what we call the heart. Please note that the smooth muscles and the cardiovascular muscle are involuntary, whereas the skeletal fiber muscles in each muscle, for the most part, are voluntary. Please note that each muscle can apply force in only one direction. Joints that move in more than one direction must be controlled by another muscle that is somewhere else. So if you look at your arm that is able to do various things and move in various directions, it's not one muscle that's controlling the directions to the left and to the right and up and down. It is other muscles that work in tandem with it. We also have fast muscles and slow muscles, and these are the two basic types of skeletal muscles. The fast muscles are those that are known for their fast contraction and also a quick relaxation. These muscles are capable of generating a lot of force and quick movements, such as jumping like a track team member, but they're also known for getting tired quickly. Think of a cat. A cat is able to generate a lot of impressive and cover a lot of ground impressively. However, they do not really last long if they were to go on its chase. Slow muscles, they contract and relax slower, and these are typically slower and weaker, but they're able to bring about a sustained contraction. That is to say that they do not get as tired as fast. These are richly vascularized, and that is to say that there's a lot more blood flow in there. If you've ever seen pictures of muscles or the body within there, you may be able to appreciate the different color in the muscles. There are some that are a little bit more white or more like pink color, and then there are some muscles that are very, very red, and those that are red would actually be slow muscles, and those that are not so red would be fast muscles. There are many skeletal muscles that belong to one of two categories, either flexors or extensors. Flexors are those that are able to bend or flex a joint. Like your biceps are able to bend your arm at the joint where the elbow is. And extensors are those that are able to straighten or extend, and in this case it would be like the triceps that are able to extend your arm. So again, the flexors are able to, the bicep allows you to bring in your knuckle closer to your shoulder, whereas the triceps take your knuckle and arm and hand away from your shoulder. We also have synergistic muscles, and those are any two muscles whose contraction produce the same movement, either flexion or extension, and quads are an example of that. Whether they contract or not, they actually bring about the same movement. There's not a lot going on there. Antagonistic muscles are any two muscles that act in opposition. For example, biceps and triceps. You're able to see how the biceps get my knuckles and my fists closer to my shoulders, whereas the triceps would extend or straighten my arm, therefore taking my knuckle away from my shoulders. As fascinating as the skeletal muscle activity is, please note that it is not completely independent and running on its own. There's actually continuous monitoring by two kinds of receptors, what we call the Golgi tendon organs and muscle spindles. Golgi tendon organs are embedded in tendons, and they connect each skeletal muscle to the bone. These are responsible for detecting the tension of the muscles. And so whenever there's a pull of the muscle on the tendon, it provides the central nervous system with information about the amount of muscle tension that is there. If there is a good amount of muscle tension, then it simply would allow for acetylcholine to continue to be pumped from the nervous system so that the muscles could continue to flex. But if the muscle contraction were to reach an extreme level, then the Golgi tendon organs would serve as a protector of the muscles, where the Golgi tendon would excite inhibitory interneurons in the spinal cord that would cause the muscle to relax. In most cases, you would see the individual with the exhaustion just give up, but if for some reason the individual has the mindset of a warrior and doesn't really care much about his body, they may push it beyond its limits, and so we would see the individual sometimes collapsing. You may have seen this in marathons where individuals that have been running for an extended period of time would have stopped running, and you see their legs just starting getting very wobbly, and this is what's often referred to out there as getting rubber legs, and that is to say that there isn't a lot of strength holding them up anymore. That would be a protective function by the Golgi tendon organs that would prevent any serious damage to our muscles. Muscle spindles are embedded in the muscle tissue, contrary to Golgi tendons that were embedded in tendons, and these detect changes in the muscle length. I'd like you to think of muscle spindles as stretch receptors within the body of a muscle, and so they primarily detect changes in the length of the muscle as in how stretched out they are. They do convey the length information to the central nervous system via afferent nerve fibers. And based on the information that is sent over to the brain is able to determine the position of body parts and bring about a response that would also keep us healthy, either by regulating the contraction of the muscles or by activating more motor neurons so that we could resist muscle stretch. Additionally, please note that muscle spindles are made up of intrafusal muscles. And intrafusal muscle fibers are basically skeletal muscle fibers that serve as specialized sensory organs for proprioception, and that is our ability to detect the amount and rate of change in a length of a muscle. You may remember proprioceptive responses through which you and I are able to detect our positioning or the positioning of our body. You may remember the example of the sobriety field test by police officers where they ask individuals that may be under the influence to put their finger on their nose, and those that are not under the influence, they may actually put it right where it is, whereas those that are under the influence would miss it by a significant margin. Please note that all the motor responses seem to be consistent with a message that is coming down from the higher levels in the hierarchy. If healthy and if all alert and aware, we would have a response that would be more adequate. If not too alert and under the influence of some substance, we would see a response that would be somewhat distorted. Here we can appreciate a very interesting response that does not necessarily make its way up to the brain, as it is not necessary to involve the highest level of the hierarchical organization in this process. You can see the finger here that gets injured by accidentally touching a thumbtack. This would produce a burst of firing in sensory neurons, afferent neurons, that are sent over through the dorsal horn and the spinal cord. This would activate the burst of firing of the sensory neurons to excite the bicep motor neurons. This would allow the muscle to contract, as it would actually bring this closer to the shoulder. Simultaneously, however, there would be also a burst from the spinal cord as well that would inhibit the interneuron. So while this actually excites, this inhibits, and this would allow the tricep muscle to also contract. So keep in mind the bicep is actually bringing this closer, this is actually extending it further out. The simultaneous of the two brings about a contraction and relaxation that cause a rapid flexion of the elbow joint without necessarily bringing the hand too far out. The only thing that you would need right here just to be safe and get this finger away from pain is to just bring it up elevated just enough. There is no need to bring the arm all the way over here or to raise the entire arm up. This short circuit right here allows us to have a response that would keep us from danger without involving the brain. Per the example shown in the previous slide, it would seem as though the levels in our peripheral nervous system seem to have a programmed response, a pre-programmed response, so that we could take care of some necessities in an automatic fashion. However, when it gets to the highest levels, it seems to be that there is no program, that it would be consistent on the varying degrees of the stimulus and the complexity of the situation. If, in fact, it does reach the highest levels of the sensory motor system, the cerebellum and basal ganglia would then coordinate all the various programs that would be received from seeing and from hearing and from tasting and touching, and based on that, it would then generate a response that we'd hope would be best. Please note that a given movement can be accomplished in various ways using different muscles. Whereas some individuals reduce their anxiety and their stress by tapping their toes, there are some that do so by tapping their arms or by engaging in a series of movements. It is believed that the central sensory motor programs have to be stored at a level that's higher than the muscle. And the reason why is because as there are different muscles that can do the same task, it would be important for the brain or something higher than the muscle to dictate what to do. The sensory motor programs may be stored in a secondary motor cortex, as again, it would allow us to understand why an individual would choose to engage in a particular movement or activate specific muscles. As I've already stated several times, behavior can be extremely complex. There's evidence that demonstrates that patients could respond to visual stimuli of which they had no conscious awareness. That is to say that if we were to ask you something and you say, well, I don't know, but nonetheless your brain may be adapting and adjusting to respond in a way that would seem otherwise, almost as if you did know. In this example here of the Ebbinghaus illusion, we actually find that the inner disk on the right, that is to say this one here, looks smaller than it really is, and it gives us the illusion that this would be bigger than this one here. Yet, they're the same size. When subjects reached to pick it up, the gap between their thumb and their finger accurately reflected the real size of the disc rather than its consciously perceived size. That is to say that regardless of the fact that it looks smaller here than here, their fingers were actually aligned with the size right here. Again, evidence pointing to how patients are able to respond to visual stimuli despite not being consciously aware. Please note that the opposite is also true. There is evidence that shows that patients could not effectively interact with objects that they consciously perceived. That is to say that they may have been aware of something that was in front of them, but yet they could not get their movement to interact with that specific part. And that would be a brain deficit for the most part, but there are also individuals that would not have deficits because of permanent damage, but also with under the influence of alcohol or a particular substance, or in some cases with individuals that may be interacting with virtual reality and with video games that would in some way alter the perception of individuals. This is a great slide to finish chapter 8. Notice how at the beginning of the chapter your brain was a lot more active in performing a newly learned sequence of finger movements, perhaps. You would be introduced to a chapter that perhaps you had little understanding of, and so your brain was a lot more active. You could see that there's a level of activity here where it just shows activity, and then you'd see that there's a lot of activity in some other components. However, after a well-practiced sequence of movements, then you start seeing that there is little activity in the brain. It starts being centralized and focused to specific parts that would allow you to comprehend the material without making use of the highest parts of the hierarchical organization. It is hoped that with more and more learning, we would facilitate a response, especially for behaviors where there may be a fight or flight response or a true emergency. However, it is also important to keep in mind that the use of the brain is essential, especially during early childhood. As we go through this process of understanding neuroplasticity, we know that it works best when stimulated. The term synaptic pruning basically means that if we do not use the neurons, we lose them. Please note that while we are demonstrating here that there is a more centralized part in the brain, we understand that our body would have learned to do this in here, and it does not facilitate for degeneration of the brain. It would simply make our functioning a little bit more efficient and better. However, again, the stated component about synaptic pruning would be more so for younger individuals.